So we learned about electron geometries and how there is 5 basic shapes for a total of 6 bonding groups possible around a central atom. But what we didn't take into account was how lone pairs can affect those 5 basic shapes. So far we were just counting every single electron group, whether it be a bond or a lone pair, we were just counting them the same as just a basic electron group. For molecular geometry, we are going to differentiate between how many bonding groups we have versus how many lone pairs, because lone pairs do affect the overall shape. So we learned about electron geometry, that just has to do with electron groups. Molecular geometry is the actual shape that the molecule will take based off of how many lone pairs you have. So anytime you hear molecular geometry, just know you are going to have to know how the lone pairs affect the shape. So yeah, EPG, you'll either hear me say EPG or EG, same thing, but it just has to do with electron geometry. Around a central atom is not the same thing as the actual structure. The structure has to do with the lone pairs. So I hope you remember that the basis of electron geometry is because of VSEPR theory, or because of what VSEPR theory tells us. So VSEPR theory is just about the fact that electron pairs are, again, very antisocial. I'm just going to keep on saying it that way. They don't like to be near each other. And we actually have an order of the repulsions from greatest to least. So you'll see that the greatest repulsions you will see is between lone pairs and lone pairs. Compared to bonding pairs and bonding pairs, they repel each other less. And then in the middle, we have lone pairs and bonding pairs. So lone pairs are the ones that really just don't like being around each other. They want as much space as possible. And then we also have the order of repulsions based off of different types of regions. So by different regions of electrons, we just mean lone pair versus triple bond, double bond, single bond. So lone pair needs the most space. Next is triple bond, which makes sense because you have a bunch of electrons, 6 electrons being shared, and then 4 and then 2 electrons being shared for a single bond. So we're going to get right into the different shapes. First, we have our derivative of the trigonal planar electron geometry. So in this case, our molecular geometry has 3 electron groups, right? But in these 3 electron groups, you have 2 bonding groups, and then we have 1 lone pair. So 2 bonding pairs and 1 lone pair. Whenever you have this combination, you will get a trigonal planar bent shape. So we're going to have another bent shape coming up, but this one specifically is trigonal planar dash bent because they're a little bit different. So the bond angle is what is mostly different. You have a bond angle of slightly less than 120, and this is due to the fact that the lone pair, so here we have an example of NO2, actually NO2 minus, this is actually nitrite, and the shape for NO2 minus, and this is the Lewis structure, so that's where we're basing it off of. We have our 2 oxygens, and then we have our lone pair on top of that nitrogen. And that lone pair needs a lot of space, so instead of it just being like linear, what happens is that lone pair pushes those oxygens down. And what we have is, instead of it just being 120 the way that trigonal planar usually is, it's going to be slightly less. So this angle right here will be less than 120 degrees. And again, it's called trigonal planar bent. It's within one plane, so it's just flat. It's just a little bent, and it has that angle to it. Next, we have our derivatives of tetrahedral. So I'm going in order. First, we started with that trigonal planar. Now it's the derivatives of tetrahedral electron geometry. So we have our pyramidal and our bent molecular geometries for these derivatives. So the first one is whenever we have 3 bonding, this should say bonding, I don't know why I wrote electron groups, but I mean, I guess we could say the same thing, but 3 bonding pairs, 1 lone pair will give you a pyramidal shape. An example of this is NH3, ammonia. In this case, you have a lone pair on that nitrogen right here, and then you have your 3 hydrogens bound to it. What it gives you is the shape of a little pyramid. So it gives you a pyramid with a triangle base, so you can see how it's outlined right here. And that lone pair, you can see the little repulsion diagram here, it's pushing those bonds down. So what you would usually see in an ideal tetrahedral geometry is 109.5, but because that lone pair repels those bonding groups, you see 107 instead. So it's just the lone pairs being antisocial, taking up as much space as they possibly can. So this is the actual molecular geometry, the actual shape to this tetrahedral electron geometry. So the molecular geometry is pyramidal for ammonia, but the electron geometry is tetrahedral because, again, EG just counts the number of things around a central atom. Next, we have our tetrahedral bent, and this is whenever we have 2 bonding groups, bonding pairs, and 2 lone pairs. So the perfect example for that is water. So water, based off of EG, it has a tetrahedral geometry, right? It has 4 electron groups around it. The usual angle for that is 109.5, but what we actually see is that oxygen has 2 lone pairs, and then obviously those 2 hydrogens bound to it. And instead of having 109.5, you will see that the bond angle is 104.5, and that's because you have 2 lone pairs now pushing those bonds down, so the bond angle gets smaller. This tetrahedral bent is also planar the same way that the trigonal planar bent is, but the angle is smaller, so that's about the biggest difference. For both of these shapes, pyramidal and also bent, the bond angle is less than 109.5 because of those lone pairs. Next, we have our derivatives of the trigonal bipyramidal electron geometry. So we have 3 derivatives for this one. And you'll see that kind of as the shapes start getting bigger based off the number of electron groups around it, that there's more derivatives, right? So there was only 1 for trigonal planar, there's 2 for tetrahedral, there's 3 derivatives for trigonal bipyramidal. So because remember trigonal bipyramidal has those 2 different positions, equatorial and axial, we have to take those things into account. And specifically, we have to take the bond angles that those axial versus equatorial positions have. So equatorial positions are the ones that will allow lone pairs, if they are present, more room. So you can see here how whenever you have a lone pair, let's say you have this compound, the lone pair in the axial position, theoretically, would make this lone pair be 90 degrees away from every single one of these bonds right here. Versus whenever you have a lone pair in the equatorial position, as shown right here, this will be 120 degrees away from that, and it will be 90 degrees away from that. So it gives it more space because compared to over here, it's 90 degrees away from everything. But right here in the equatorial position, it's 90 degrees away from this one, but then it's 120 degrees away from this one and this one. So it will prefer that. It gives it more space. So I'm going to show you the actual shapes on the next slide, but these are the shapes that we can have when you have 4 bonding groups, bonding pairs. Just trying to make it kind of clearer. So when you have 4 bonding pairs on 1 lone pair, you get something called a seesaw. You'll see why it's called like that. And then 3 bonding pairs, 2 lone pairs, T-shape, 2 bonding pairs, 3 lone pairs, linear. So the bond angles, again, will be decreased in comparison to what we consider like the electron geometry bond angles, or whenever you have no lone pairs. Let's go ahead and take a look at these. So again, this does not occur. What you will actually see whenever you have 1 lone pair and 4 bonding pairs is something called a seesaw shape. So the molecular geometry is seesaw for 4 bonding pairs and 1 lone pair. So that lone pair takes that equatorial position. And then if you kind of turn your head around and look at this, you'll see that you can see that little seesaw shape. And just imagine that like one person sat on one end and the other person sat on the other. It would be like a little seesaw that you can play on, like a playground one. So that's where that name comes from. Next we have whenever we have 2 lone pairs and 3 bonding pairs. The electron geometry, again, these are all electron geometry of trigonal bipyramidal, but the molecular geometries are what's different, okay? So notice that. So for this case, 2 lone pairs and 3 bonding pairs, we will see that the next lone pair takes up another equatorial position, and what you end up having is something shaped like a T. So it's just flat, shaped like a T, that's where that name comes from. And then finally, whenever you have 3 lone pairs, they take all equatorial positions because that gives them the most space away from each other. And what you end up seeing is something called linear. So it looks like the regular linear, except we have those, be aware of those 3 lone pairs. So those are the 3 derivatives for trigonal bipyramidal. So just a big, something to note. Oh, sorry, I didn't write this. It's 3 lone pairs and 2 bonding pairs. Something to note and just be aware of, so this is something I'll test you on, is where the lone pairs start taking places. And that is always equatorial, never axial. So you'll always see the lone pairs take the equatorial positions. And then finally we have our derivatives of the octahedral geometry. So whenever you have derivatives of this electron geometry, you will either see a square pyramid shape or a square planar shape. So for square pyramid, you have 5 electron groups and 1 lone pair. And here is our example. So we have BR, what is this, F5? Yeah. We have that 1 lone pair, and all of these positions are equal, as I stated on that previous video about just electron geometries. Every position for octahedral outer atoms on a central atom, like that's the electron geometry around that central atom, all the positions for the outer atoms are equal. Like if you turn this thing around, it's going to be exactly the same. The position is always the same. It's like they're all, I wish I had like an example of what type of shape this is, but they're all the same. So you can just say, okay, it's taking that position at the bottom. And then what you see is a little square pyramid. So the reason it's called a square pyramid is because the bottom of it, the shape of the base, is a square. So you can see it right there, and then it forms like a peak up here, so it's a pyramid. So the bond angles will be less than 90 because of that lone pair. It's pushing those bond angles up. And then for whenever we have 4 electron groups and 2 lone pairs, you will get a square planar shape. So in this case, in order to take a position that is the farthest away for the lone pair, it will take the one that's completely 180 degrees away from it. So what you will have is just a square, a plain square, like it's flat, and the shape it forms from the corners, right, the atoms, will be just a square. And again, bond angles will be, for this one, it will be 90 because they push kind of the same, the lone pairs, so it stays the same. Here is a nice little table that summarizes all these shapes. I would really recommend using it. I have it on the lab about molecule shapes. You can use it. It has some nice examples, so I'm just kind of going through this. And it also has, what I like about it is that it has both the EG, so here are all the EGs, and then here are all the MGs. So you can compare those two and kind of start being able to recognize those. So how do we determine these two things? We already practiced determining EPG. Again, remember EPG and EG are the same thing. We already practiced determining EG. Now let's practice determining the MGs. So it's a very similar, same process almost. You draw the Lewis structure, you determine how many electron groups you have around the central atom, and then you determine how many are bonding versus lone pair, and then we use that table and just determine the shape and the bond angles. So one thing I do want to talk about before we start practicing that is something you will see In the textbook, when you Google things, whenever you are watching YouTube videos, you will see these things and you probably might not know what they are. And I actually had a few Lewis structures that had these little wedges and hatched and solid wedges, and you were probably confused about what they were. But I do want to talk about it because also you're going to see this in organic. So if you understand what these mean right now, then it will save you a lot of trouble whenever you get there. So the hard thing about drawing things on paper is that how do you show the actual dimensionality? By dimensionality, we mean how do we show something in 3D on a plane, like on one plane of a flat piece of paper. So what we do is that we have a convention of just drawing the central atom in the plane of the paper. And then if you're symbolizing something, an atom that's bound to that central atom, as also being in the plane, you will draw it with a straight line. Whenever you have something going into the page, so behind that central atom, you will draw it with this hatched. I also hear hashed. I honestly don't know which one's, it's probably the same thing. So hashed, hatched, same thing, but it's the little lines. And then for something going into in front of the plane, so towards you, like towards your face, let's say you have a paper in front of you and something is going towards you, like towards your nose or something, that will be symbolized by a solid wedge. So let me just draw something real quick. So we have, for example, PCl5. One of them will be hashed, whatever, and one of them will be solid. The reason for that is one of these, this is trigonal bipyramidal, so these on top, these positions, the axial positions, they just go straight up and down, so you can consider them in the same plane. One of these will go also in the same plane, and this one of them goes towards you. I should have drawn these the other way around, but one of them goes towards you, one of them goes behind. So it forms kind of like a triangle. So this is how we show things in 3D. It's very difficult to visualize. I hope that the molecule shapes lab really helps, because truly that's the only way for you to virtually see it, and if we had actual molecular model kits, but unfortunately we don't have that right now. So please take advantage of that simulation that you'll use for that lab. Okay, so let's practice determining the Eg and Mg. We have carbon dioxide and boron trichloride. Let's draw the Lewis structure real quick. So for CO2, we have one carbon. Carbon has 4 valence electrons. For 2 oxygens, we have 2 times 6 valence electrons. So I have 12 plus 4, that's 16 valence electrons. Whoops. So carbon is going to be my less electronegative atom, which means it's our central. Also, it's just a single atom compared to 2 oxygens. We're going to start off with our single bonds, and then we start adding electrons to our outer atoms. So far we have, to complete the octet, so far we have used 8 and 8, that's 16. So we used up all of our valence electrons. But now we notice that carbon doesn't have an octet. So what we need to do is move some bonds over, and I'm actually going to move 1 and 1 bond so that we have a total of 4 bonds around carbon. And then oxygen, those oxygens still have those lone pairs, and everything has an octet, everything's happy now. So how would we determine the Eg and the Mg? So the Eg, did you guys hear that thunder? So the Eg, we just look at the number of groups. So there are 2 electron groups, which means we have a linear Eg. And then for Mg, we look at the types of groups. We have 2 bonding pairs, and that's it. So because we have no lone pairs, anytime you have no lone pairs, your Eg and Mg will be the same. And then for boron trichloride, so this is, I kind of brought up some naming, testing if you know how to convert names to formulas. So boron trichloride, we have 1 boron, that's 3 valence electrons, and then we have 3 chlorines, we have 3 times 7 valence electrons. So 21 plus 3, that's 24. So boron is going to be our central, and then we're going to start off with single bonds to those chlorines. So then you start distributing atoms. And remember, boron is one of those exceptions that can have less than 8 electrons around it. It's fine. So far we have used up 6, and then, well, 6 times 4, that's 24. So we're done. Everything has an octet besides that boron. It's okay. It's one of the exceptions. Okay. So how many electron groups do we have around this boron? We have 3 electron groups. And again, these are kind of boring examples because there's no lone pairs, but 3 electron groups, that's trigonal planar. And then we have no lone pairs, so it's going to be the same thing. So that's the EG. And then for Mg, again, no lone pairs means it's the same thing. So you just use your table. Like let's say I had 2 lone pairs around the central atom plus 2 bonding pairs. You look on the table, and I don't have it here just because it takes up a lot of space, but you look on the table, you look for the row that shows you an example with 2 lone pairs and 2 bonding pairs, and then you're like, oh, okay, so this is for EG, this is tetrahedral, and then for Mg, this example that I'm just randomly brought up, would be tetrahedral bent. So again, just get acclimated with that table. It is your BFF with determining EGs and MGs.